This video will show the step-by-step solutions for the final exam review questions. There will be a small pause at the start of each question to allow anyone watching the video to fast forward to any particular questions that they would like to view. Question 1 in our review comes from section 1.3. This was our problem-solving section. There's two key skills that are coming through in this question. One is the problem-solving process, and that if you're presented with a problem, can you understand it well enough to develop a plan and carry out that plan to reach your answer? And this question will also involve operations with fractions, which was another key topic in Chapter 1. The problem reads, the gasoline gauge on a van initially read 1/8 full. When 15 gallons were added to the tank, the gauge read 3/4 full. How many more gallons are needed to fill the tank? One problem-solving approach is to draw out or diagram out the situation so that you can understand the question better. So here I can draw my gasoline tank, and it was already 1/8 full when we started. We added 15 gallons of gas, which put it at a new level showing 3/4 full. And we want to know how many more gallons are needed to fill the tank. So we want to know what is needed in gallons of gas to fill our tank. So now that I have an understanding of the situation, we're relating a tank and how full it is to how many gallons of gas are in the tank. We can now do some operations. So one thing I want to figure out is these 15 gallons that I added, how much that actually changed the level that my tank was at. So I want to know really the difference between these two, from 3/4 to 1/8. How much did that 15 gallons actually fill up our tank? So to find the difference in two numbers, that's subtraction. So I want to know what's the difference between 3/4 and 1/8. Now here, I could type this directly into my calculator, but it's easy enough to do by hand as well. To get this figured out, we need a common denominator when you add or subtract fractions. This is fourths, the other one's eighths. I can really easily make 3/4 into eighths by multiplying the top and the bottom of my fraction by 2. By doing that, I'm going to get the equivalent fraction, but with that common denominator of eighths. It's 6/8. So 6/8 minus 1/8, 6 minus 1, that leaves me with 5/8. That was how much our gas tank changed by adding those 15 gallons. So we know that 5/8 of the tank was filled by 15 gallons. Now I want to go ahead and figure out what's left for me to still fill the tank with. So we have it currently at 3/4. I want to fill it up all the way. So one full tank minus 3/4 means that there's 1/4 of the tank left to be filled. If you weren't sure where I got 1/4 from, in my head I was just thinking that 1 is the same thing as 4/4. To get our common denominator of fourths, 4 minus 3 leaves us at 1/4. So I know that 5/8 can be filled with 15 gallons. So now the bigger question is, if I want to fill only 1/4 of the tank, how many gallons of gas that would be? So what we have right here is actually a proportion, which we saw later on in Chapter 6. You can solve it without creating a proportion by scaling up or scaling down our relationship between the 5/8 of the tank to 15 gallons. So I could say multiply by 8 and then divide by 5 to figure out how many gallons of gas are needed for just a single tank, and then scale it down once again to make 1/4 of a tank. So you could just multiply and divide your relationship of the 5/8 of the 15 gallons to figure out your result. But now that we're at the end of our course, we have more skills that we can use. So one of the skills that I can use is the proportion. So you know you have a proportion on your hands when you're comparing 4 items, and specifically there's some concrete relationship between 2 items that you're then recalculating for some new quantity still involving the 2 items. So here what I'm comparing is my tank capacity, right, 5/8 or 1/4, to the number of gallons that are filled. So 5/8 is being compared to 15, 1/4 of the tank to some unknown amount of gallons. So that is our proportion that we want to go ahead and solve. So like any proportion, you can cross multiply. So 5/8 times x and 15 times 1/4. And yes, there are fractions there, and that's totally fine. Fractions are just like any other number. You can operate with them. So if I did 15 times 1/4, that's 15/4, and 5/8 x. And then there's a whole variety of ways that we can continue from here. I could divide the 5/8. One trick that we also talked about many times was to get rid of denominators. On an equation, you can multiply the denominator. So if I multiply both sides of my equation by 8, that will fix the 5/8 for us, and then it will also fix the 1/4 as well. So there's a factor of 4 inside of 8 that would divide out, leaving a factor of 2. 15 times 2 is 30, and then we can divide out the 5. And the relationship that's revealed is that we need 6 gallons of gas. So whatever approach you took, if you use proportions or if you use the scaling up or scaling down idea, you want to make sure that you show your work. You want to make sure that your final answer is clearly stated, and you definitely want to make sure that you include any units on these problems. If you leave off the units on your answer, that is points deducted. Problem 2 comes from section 1.4. Section 1.4 involved interpreting graphs and reading graphs. And so here we have a line graph that we want to go ahead and read. Looking at our axes, we can see that years are being related to a percentage, and that the percent is the percent of students who return for the second year of college at a 2-year public institution. So the first part of our question is what percentage of students return to college in the year 2010. So looking at my graph, I would look at 2010 and then identify the height of my point. Now this particular point that we're seeing here, it is not on one of our lines. It's somewhere between 55 and 56. So we need to do our best to estimate where that would potentially lie. So one trick that you can take is to divide the interval between your tick marks in half and use that to help you estimate. So if I divide this in half, we can see that it's definitely above the halfway mark, maybe kind of around the midpoint there. So half of the distance between, this would be 55.5 to 56, right? We could say something like 55.75. That would be a reasonable number. But here, because we don't have much more information, it really is an estimate. So anything kind of between 55.5 up into 56, but not including 56, would be a reasonable estimate. The reason why we can't include 56 is because we definitely can see that our data point is not on the line for 56. So it's going to be some estimate kind of between the halfway point, which is 55.5, and then the next line on our graph, which is 56. So this will be an approximation. We do want to include units. This was a percentage. So if you leave off your units, you will also lose some points, some partial credit on the exam. Part B says, during which years did the percentage of returning students decrease? So now I'm interested in looking at the pattern in between each year and specifically looking for a decrease. So a decrease would be indicated with kind of a negative sloping line. So we can see a decrease occurred between 2006 and 2007. Then it is a positive sloping line, so it would be an increase for the next set of years. The next set of years kind of remained flat, so that kind of looks like a zero change. then we saw an increase in the next set of years, and then a decrease again. So they said, in which years did the percentage of returning students decrease? Well, there was those two intervals. There was the section between 2006 to 2007, and there was also the section between 2010 and 2011. Part C says, between which years did the largest increase in the percentage of returning college students occur? So here we want to know the increase, but we also want the largest increase. So to determine the largest increase, we're going to have to look at the sections of our graph where we saw an increase and actually calculate what the values changed from. So what we could do here again is estimate. I can see that this first point for 2007 was right around maybe 51.3. Again, we need to do our best to kind of estimate that number. And then for 2008 was about 53.6. So I would look at the difference between those 2 years. So 2008, it was 53.6. 2007, 51.3. I would go ahead and subtract those, and I get 2.3. The next set of numbers, we can estimate in the year 2010. I'll use the 55.75 I got here. And at 2011, that's a decrease here. So we want 2009. So 2009, I'll call it 53.75, something like that. So from 2010, which we said was 55.75, to 2009, which was 53.75, we're seeing about a change of 2. So between those two, the larger value would be the 2.3 that we're seeing here. So the higher value, that's going to be the largest increase. So that was between 2007 and 2008. Question 3 comes from section 6.3. That was our section involving operations with fractions. So we know that we're going to be seeing some operations with fractions here, and we want to be able to show that we are able to do those operations even without a calculator. So we can see there is a pie shop that's using a simple pie crust recipe that calls for ingredients of flour, butter, water, and salt. We can see 3 crusts, has a certain amount of cups, butter, water, and salt, and then 5 cups is a different amount. And we want to know how much of our ingredients, the flour, the butter, the water, and the salt, will be needed to make 4 pie crusts. So we have given in our table 3 pie crusts and 5 pie crusts, but we need to find the value in between, which is 4. And they said to leave our answer in the proper fractional form. That's like the 3 1/3 or 4 1/2 or 7 1/2 values that you're seeing in our table. Those are the proper fractional forms where you can see the whole part and then the fractional part that will be less than 1. So there are several different approaches that we could take with this one. One option would be to take either the 3 pie crust measurements and perhaps scaling them down to how much is needed for 1 crust, and then scaling them up again for how many is needed for 4. So that would be division and multiplication occurring to our values. That's one option. Another option is we can notice that 4 lands in a very special place between 3 and 5. It's exactly in the middle. And when you want to calculate the middle number between 2 numbers, you can do that very easily with an average. So I can find the average value for the flour, the butter, the water, and the salt, and that will tell me how much I need for the 4 crusts. So I'm going to go ahead and organize this because we do have several different parts to our answer. So you may want to be very clear, if that happens on the exam, labeling which answer goes with which piece. So first I'll calculate flour. So to calculate the average amount of flour between the 3 crust and 5 crust values, I would add up the numbers that are given to me, and I would divide it by 2. Now, the 3 1/3 is not an easy number to work with in our calculation. So we usually turn that into the improper fractional form, which is just a certain number out of 3. So I can do that. The trick is to kind of do it by hand. That doing in the calculator is actually more work than it's worth. So how you change a proper fraction into an improper fraction is you're going to multiply the bottom of your fraction by the whole value, right? So we're going to multiply 3 times 3, that's 9. And then you're going to add the value on the top of the fraction. So I got 9 when I multiplied, add 1, that is 10. So 3/3 is equivalent to 10/3, and the 10/3 is going to be far easier to use in any mathematical calculation. So I'm going to actually replace where I had my value for the 3 1/3 with the 10/3. It's going to just make it so much easier to calculate. So now from here, I need to go ahead and add the numbers on top of it before I divide by 2. I could do it by hand by getting a common denominator. 2 is the same thing as 6/3, which when I add to 10 will get you 16/3. The other option is I can type it into my calculator. Depending upon the type of calculator you have, it may change the decimal answer that you get into a fraction by hitting different buttons. So whatever calculator you use, make sure you know what buttons to press to get that. The other thing to be cautious about when working with fractions is that you type it in inside parentheses. In general, I do that for all my fractions, just to be paranoid and make sure that it always knows that I'm talking about that fraction when I show my division. So here I can type in my 10/3 inside parentheses, just to be safe. Your calculator will give you back a decimal answer, and then hit whatever series of keys you need to give you back your fraction. And then we'll go ahead and divide by 2 now. So I can do this by hand as well. The trick when you are dividing values that involve a fraction is you're going to multiply by the reciprocal of the denominator. So here I have a 2. The reciprocal of 2 is 1/2. So that would multiply across the top. 1 times 16 is 16. 3 times 2 is 6. So I get 16/6. That can then be reduced down to 8/3. So I could do it by hand. If I chose to use my calculator, I would take my previous answer, divide by 2. So if you had it as the last line of work on your calculator, you can use the answer key. If it wasn't your last line of work, then you definitely want to make sure that you do the parentheses, 16 divided by 3, closing your parentheses, and then divide by 2. So you'll get that decimal answer, and you'll have to convert it back to the fractional form. So I have my answer. The problem is it's not in the correct format. We want not the improper fractional form, we want the proper fractional form. So you can find that by doing long division. So how many 3's there are in 8? There's 2 of them. That gets you a value of 6. And then there's a remainder of 2. So whatever you divided out, that's going to be your whole number piece. The number that's left is going to be your remainder of the same fraction that you had earlier. So 8/3 is the same thing as 2 2/3. Again, I need to label my answer. So we're talking about cups for our flour measurement. And just to be really sure that the reader of my work knows what I'm talking about, I'm going to label it with what I was talking about, that's going to be the flour measurement. All right, now we can look at the next ingredient, which is butter. So the same idea applies. I can do the average of the 9 tablespoons and 15 tablespoons from our 3 crust and 5 crust recipes. Now this one does not involve fractions, so it's a little bit easier. 9 plus my 15 is going to get me 24, which we will then divide by 2. That divides evenly to 12. Again, I want to include units. Without units, I'm not going to get full credit. So this is tablespoons of butter. Same thing now, we're going to do it for water. I have fractions again, so when we do our average, we're going to be careful with our fractions. So I want to do 4.5 added with 7.5, and then divide by 2. So here I have a couple different options. Because my fractions are halves, the decimal values are actually pretty easy to work with. The 10/3, the decimal number is not good to work with because it's that never-ending value of 3 at the end. So we can't write it in the decimal form without rounding it, and then that's going to create problems for us. But I can exactly write down 4.5 as a decimal by doing 4.5. So as long as your decimal value is not actually needing to be rounded, you can still write it down exactly and it's fine. It's the same thing as if you wrote the fraction. So if I preferred, I could use 4.5 and 7.5. It just makes it a little bit easier to do our addition. When you add those up, you get 12. When you divide it by 2, that gets you 6. For our water, those are tablespoons. And then last but not least, we'll do salt. So salt, I had 3/8 and 5/8. I want to make sure that I remember that before I scroll down. Oops. Actually do it in here. Salt. So the average, I'm going to add them up. Before I divide by 2. Now this time they're both with a common denominator, so adding them is fairly easy. They're both eighths, so I can do 3 plus 5, that's 8/8, or a value of 1, right? That reduces down to 1/2. So it's going to be 1/2. I want to make sure that I have the correct units for my salt. Those are being measured in teaspoons. So I have all of my work shown. I have it organized. I have units on my answers. All my answers are clearly labeled by being circled. Problem 4 comes from section 6.5, which involves converting measurements in the metric system. Here we want to make sure that we have our conversion values that were given in that note section included on our reference sheet. So as you can tell, we're going to need to convert between centimeters and hectometers, ounces and grams, quarts and fluid ounces, yards and square yards and square feet. So some of those values you may know how to convert without any assistance, but a lot of these require specialized values to do the conversions. So make sure you go back and look at those section 6.5 notes. There was 2 tables that had some conversions on there. Make sure you include those conversion values on your reference sheets so that way you have those handy for performing these problems. So the first question is going from centimeters to hectometers, and those are both in the metric system, and the metric system works off of this place value system with prefixes. So the largest unit is kilo, and it could be kilograms, kiloliters, kilometers, depending upon whether we're measuring distance or volume or mass. Then the next largest is the hecto, followed by deca. Then right in the middle is your base unit. So here we're talking about meters, right? If I was talking about liters, that would be my base unit. If I was talking about mass, then it would be grams. So in the middle of our scale is your base unit and whatever you're measuring in. And then the smaller values are the deci, the centi, and the milli. So right now, our number is a centimeter. So I'm right here in my sequencing, and I want to make it into a hectometer, which is here on the left. So just like I need to move kind of from one part of my table here to the next, I'm moving to the left. We're going to do the same thing with the decimal point. So I need to move it 1, 2, 3, 4 places to the left to travel from centi to hecto. So we're going to do the same thing on our number. I'm going to move my decimal point 1, 2, 3, 4 places, and the new location is going to be the value of our number. So that's 0.57. If you want to include the extra 2 zeros at the end, you can, but they're unnecessary in a decimal number like this. And then I want to make sure that I include my units. This is now measured in hectometers. Part B, we want to go from ounces to grams. So I would definitely need to pull up my reference sheet and look at what's the relationship between ounces and grams, because ounces is in the standard English way of measuring units and grams is in the metric system. So it's going to be a weird conversion number. Those are usually decimal values because you're going from one system of units to the other. So 1 ounce is equal to 28.3 grams. So that's the conversion relationship that we need. Now this one, I'm going to use dimensional analysis to help me convert it, so I know whether I need to multiply or add this 28.3 to my 150. And how dimensional analysis works is you start with the number that is given. The number that is given for me is 150 ounces, and I'm going to make it a fraction. It's not naturally a fraction, and so the easiest way to make it one is to stick it over a value of 1. So now I've made it a fraction, and then I'm going to multiply by another fraction that's built off of our conversion factor. So I'm going to put ounces, the 1 ounce in some part of my fraction, and then 28.3 grams in another part of my fraction. Now, and where I decide to place it is guided based off of what we already have. So I have ounces right now in my numerator, and I don't want ounces to stay. I want to get those canceled out. I want those to go away. So to do that, I need to place my ounces in the bottom of my second fraction. By doing that, I now have a common value of ounces in the numerator and the denominator that would cancel. And then I would end up getting a result that is in the grams, which is what we want. So dimensional analysis, that's how it works. You take your given number, write it as a fraction, multiply by additional fractions from your conversion values, set up so the values you don't want cancel out and the values you do want stay. And then I'm going to just perform this multiplication. So when you multiply fractions, you multiply across the top. So 150 would get multiplied by the 28.3. That is 4,245. On the bottom, it would be 1 times 1. But dividing by 1 doesn't change the value of my number. So in the end, this ends up being the same 4,245, but now in terms of grams. Part C will be a similar setup. I need to convert quarts to fluid ounces. Now this one is not going between two different units of measure, like our last example. We're still in the standard unit of measuring. We're just going from one representation, which is quarts, into fluid ounces. So I'm going to start by writing out the given number, 1 quart. And I know I eventually want to get to fluid ounces. The tricky part is that if you look at your conversion formulas, there's no formula that directly goes from quarts to ounces. The only relationship that would be helpful for us is quarts to pints. So I'm actually going to convert my quart into pints and then work my way towards the fluid ounces. So 1 quart is equal to 2 pints. So similar to the last section, I know I needed to place quarts in the bottom so that my quarts unit of measure would cancel. So this would now be in pints, but that's still not what I want. I want fluid ounces. So I'm going to keep working towards that fluid ounces. So then my next fraction, I can't do much with pints except make them into cups. So 1 pint is equal to 2 cups. So I placed it again so that the pints would cancel out. And then I still don't want cups, I want fluid ounces. But the good news is I've gotten there now because I know that 1 cup is equal to 8 fluid ounces. So this one required a couple steps along the way. And that can happen sometimes. There may be in-between measurements that you have to travel through to get to your final unit of measure. The beautiful thing about dimensional analysis is it allows us to take care of that in one setup. So what's going to end up happening is I'm going to multiply across the top. 1 times 2 times 2 times 8 gets me 32. And across the bottom, 1 times 1 times 1 times 1 is 1. 32 divided by 1 is still 32. and my units were fluid ounces. Part D, I want to convert 10 square yards into square feet. So here the thing that's tricky is we're dealing with square units of measure. That typically occurs when you're dealing with things like area. So maybe I have area of a particular floor that's 10 square yards, and I want to convert that to square feet. So to do that, I can convert to feet. The trick would be that I'm going to need to do it multiple times because I actually have 2 yards. When we say yard squared, that's actually 2 yards multiplying by themselves. That's what we mean by the square. So we have to take care of both of those yards. So I'm going to include 2 conversion factors. The relationship between yards and feet is that 1 yard is equal to 3 feet. I need to do that conversion not just once, I have to do it twice because we had square yards. So because I see yard squared, I need to actually have 2 yards that need to cancel to get rid of that. So I'll multiply across the top. 10 times 3 times 3, that's 90. The bottom is 1 times 1 times 1, which is 1. 90 over 1 is 90. And then my units, if you notice we have feet times feet, that's where the square feet come from. So our final answer will be 90 square feet. Problem 5 also comes from section 6.5. And that's because we're going to be looking at percentages. So percentages were also in our section 6.5. After 1 year on the job, Grady got a raise from $10.50 an hour to $11.34 per hour. We want to know what is the percent increase of his hourly wages. So we know we want our answer as a percentage. So this one, we know it's an increase. We can see that. He increased his overall wages from $10.50 to $11.34, but we want to know what percent change it actually was. So when you want a percentage change, you're going to calculate the difference between your 2 numbers, and you're going to divide by the original value, whatever you started with. So my difference, right, I would want to go ahead and subtract this in an order that will keep it positive. So 11.34 minus 10.50 divided by my original amount. So my original amount is what I started with. In this case, it's Grady's original pay amount, which was $10.50. And that's the important piece, that when they are talking about a percent change, like this percent increase, you have to divide by the original amount, whatever you started with. Because it did change, right? It either went up or potentially down, but you're always comparing it to what you started with, what the initial value was. So when I subtract, I get 84 cents on the top, divided by 10.50. I'm going to get a decimal number. I get 0.08. And we want a percentage. So remember that percentages are really decimals that we've just converted into that percentage writing. So 0.08 I can make into a percentage by multiplying by 100 or moving my decimal place to movements to the right. That does the same thing as multiplying by 100. And that is 8%. Problem 6 is also from section 6.5. So we can see there's a lot of material coming from 6.5 that might be an important section to review in preparation for the final exam. This one, we have Daniel bought a new smartphone that retails for $900. We want to know what is the cost of the phone if Daniel gets a 10% friends and family discount. That's part A. And then part B is what is the final cost of the phone including the discount and a 8.25% sales tax. So we're first going to look at the 10% discount. And this one we can potentially get our answer 2 different ways. One way is to figure out how much needs to be deducted because of this 10% savings. So what I could do is find 10% of the 900. Now 10%, that is not the way it's normally written. This value in real life is a decimal. It's 0.10. So when you have it written in the percentage form, you need to make sure that you convert that into the decimal form before you do any math. If you're going to do any math on a percentage, you have to write it in the decimal form. How I could get from 10 to 0.10, that's dividing by 100. That's 10 out of 100. So that's my decimal value, and I'm going to multiply it by whatever number I want to find a percentage of. I want to know 10% of the 900. So I'm going to multiply my decimal, 0.10, times my total, 900, and that gets me 90. Now here's the thing, that 90 is only my discount. That's only how much I'm getting off of my total. So I still have to take my original amount, the 900, and subtract my $90. And that's going to get me $810. That'll be the new sale price. So I had to do two things here. I had to calculate what was 10% of the $900 cost, and then take that away from the total of 900 to get our new value. The alternative way that I could have solved this is in one step. It's a little bit faster, and that's where we don't calculate what's coming off of our bill, but rather we calculate what would still remain. So if I'm taking 10% off, that means I'm going to keep 90%, right? Or 100% minus 10%, that's our 90% of my phone's value. And I can calculate the 90% in the same way I did the 10%. You would take your decimal representation, so 90% is 0.90, and I multiply it by my total, which is the 900. And when I do that, I'm still going to get the 810. I just got there a little bit faster. So I didn't have that in-between step of calculating the $90 discount. Now part B is building off of this, so once I have applied my 10% sale, we want to now include sales tax. So sales tax, that's not a percentage off, that's a percentage that gets added on. So I can calculate it in a similar manner. I can figure out how much the tax would be and then add it onto my bill. So 8.25% is 0.0825. If you weren't sure how you got that, again, just take your percentage number and divide by 100. So 8.25 divided by 100 gets us that decimal value. Times our total. Now the total I'm calculating our sales tax on is not the original 900, right? We got a discount. Now the new price is 810. So the 810 is what we're going to calculate the sales tax on. And this one, when I type it in, I'm not going to get a perfect decimal. We may have to round it, so I'll show that here. So 0.0825 times 810. We can see we get 66.825. Now when we're talking about money, which we are here, we only include two decimal places for the cents. So I wouldn't do the 82 because my next digit is a 5, so we would use our standard rounding rules. This would have to round up to 83 cents. So keep that in mind when you're dealing with money. You may have to round up or down to include the two decimal places. So that is my tax amount. And again, that's not the end. You got to add the tax to your sale amount, which is our 810. So 810 adding the 66.83 gets me my final total of $876.83. Now, similar to the last problem, this can be calculated a little bit more quickly as well. Instead of calculating the tax separately and then adding it to our total amount, we can do the tax all together. And how we would do that is we would be essentially looking at, how much tax is exceeding the original value. So if the original value was 100%, adding the 8.25% sales tax would mean I want 108.25% of my original value. So I'm just taking 100% and adding on the 825. That's essentially what we're going to do here. So if I took my 108.25% and wrote it as a decimal, that would be 1.0825. I'm going to multiply that by our previous total, which was 810. And when we do that, we're still going to get the same number. Again, we have to worry about rounding. So to show that for you, 1.0825 times 810. Right, there's our 875 point, and then we would round the 2 decimal places. It would be 83 cents. So whichever method you choose is fine on this. Just make sure that you show your work and that you're clearly showing your final answer. Make sure you throw your dollar symbol at the front of your statement, so that way we can see that we're talking about money here. Problem 7 comes from section 7.1, which was looking at solving equations. So here we have the area of a triangle represented as capital A is 1/2 of the product of the base of the triangle lowercase b and the perpendicular height lowercase h. And they gave us the same formula that they just described. Area equals 1/2 base times height. You may recognize that from our geometry unit. But we want to manipulate this equation and solve for the height h. So what I'm going to do is write down my original equation, and we want to use our algebra rules to get the h by itself. Now this one is particularly tricky because we have a fraction involved. We have the 1/2. So you can take a trick that I've shown you guys, I'm sure many times, that's very helpful, which is when you're dealing with a fraction and you have an equation, you can multiply the denominator of that fraction on both sides of the equation, and then your fraction will go away. So here I don't want the half. I'm going to multiply both sides of my equation by 2. That will allow my half to cancel out, leaving just base times height, and the other side of the equation is now 2a. Now this is an excellent trick. You can only use it on equations though. So if you don't have an equation where you can balance it on the left and the right side, you gotta do the operations with the fractions. There's no way of getting around that. But here we do have an equation, so I can multiply both sides of the equation by 2, and that allows us to get rid of that fractional value of 1/2. So now I deal with my 1/2. I can focus on getting h by itself. So right now, h is multiplying by the value b. And when you solve an equation, you want to do the inverse or opposite operation to get your values by themselves. So if I want h by itself, I want to undo the multiplication by b. So the opposite of multiplication is division. So I'm going to divide both sides by b. That's going to cancel out the b for us, leaving just h, which is what we want. And then on this other side, I'd still have 2 times a, and that would be all over b. So you could leave your answer like that. Because 2 is a number and it's in the numerator, we also kind of have an alternate way of writing our answer. I could pull out the 2 in front and then have capital A over B. That's actually the exact same thing. It's just whether you want the 2 to stay on the numerator of your fraction or if you prefer to pull it out in front. They both mean the same thing. Problem 8 also comes from section 7.1, and this one involves equation solving as well as expressions. So equations and expressions get confused a lot, especially when you have variables involved, like this problem, but you actually do not treat them the same way. You simplify expressions. In other words, you combine like terms and perform PEMDAS until you've made it as simple as you can. But equations, you can actually solve. So those are different algebraic processes. We want to make sure that we don't get them mixed up, and so that's what this question is doing. So we first want to identify whether the statement that is given is an expression or an equation. The huge difference is the presence of the equal sign. The equal sign indicates you have an equation. The absence of an equal sign means you have an expression. So the first step would be to identify that, and that'll help guide us into what we want to do with these statements. Do we want to simplify them, which we would do for expressions, or do we want to solve them, which we would do for equations? So I'm going to start with A, which is an expression. So A means I'm going to simplify it. Simplification means we're going to follow the rules of PEMDAS. So if I see things in parentheses and I can perform operations, I want to do that. Then exponents, then multiplication, then division, then addition and subtraction. So we do have parentheses here. The thing is that 7x to the 4th, x squared, and negative x are all different terms. They all don't have the same power on the x, and so we actually can't add those up or combine them in any way. So even though I see parentheses, we can't actually do anything with that. We also see exponents. I see powers of 4 and 2 and so on, but again, nothing's really happening there, that the power is occurring to x, and x right now is just a variable. It hasn't been replaced with a value of any kind, so I can't actually perform those powers. So the p, even though we see it, didn't really do anything. Same thing for e. There is an implied multiplication here, I would argue, between the negative and the set of parentheses. So parentheses are used also as a multiplication operation, and that's kind of what's happening here. We want that implied -1 to multiply through to the 7x to the 4th, the positive x squared and the negative x. So we can do multiplication here. So what I'm going to do is carry down anything that doesn't need to change, and that's an important thing when it comes to algebra. You don't want to lose track of any of your terms, so you need to rewrite them as you go from one line of work to the next. So I'm leaving 5x to the 4th and 3x squared alone. And now I'm going to multiply through. We actually call this distribution, but it's just a fancy way of saying you're multiplying over several terms. I'm going to multiply my -1 to all the terms that we see here. So 7, when you multiply it by -1, turns into a -7x to the 4th. My positive x squared, when I multiply by -1, goes to -x squared. And negative x times the negative, that double negative is going to add into turn into addition for us. So I perform the multiplication. We technically have multiplication here between like our 5 and the x to the 4th and the 3 and the x squared and so on. However, again, there's nothing that can be done there because x is a variable. There's no value put inside, so we can't do anything further with that. So that's done. Division, we don't have any division, so that's out. And then addition and subtraction, we have tons. Those are operations you want to work left to right. And that's because the ordering does matter when it comes to subtraction, and we don't want to get the ordering done wrong. So if you work from left to right there, that'll prevent any mistakes. So working left to right, we're going to add or subtract our terms, and we can only add and subtract like terms. So that means values that have x with the same power. So I have x to the 4th here and a -7 x to the 4th there. So I can do 5 minus 7, that's -2 for the x to the 4th. Then I can look at squareds. I have 3x squared minus x squared. So again, those are like items. I can do 3 minus the 1, that's 2x squared. And then my x term is all by himself, right? There's no other x terms to combine, so he would just get carried down. And that is simplified as we can make it, so that would be our final answer for A. For B, we have an equation, and equations you solve. So we're not interested too much in simplifying, we're interested more in isolating the x. Now this one is a particularly interesting equation because we have those lovely fractions in there. So there's several ways that we could approach this. So one way I could approach it is by getting a common denominator that I have to do because I'm subtracting two fractions on this left side of my equation. So I can do that. It works just like any other fraction. You need a common denominator. Between 5 and 2, the best I can do is 10. So I can multiply this one by 2 on the top and the bottom. That will make it into tenths. Multiply this other fraction by 5. That'll get us into tenths. So if you notice, I put parentheses because the 2 and the 5 do need to distribute. So 2 will multiply through. 2 times 2, this is going to get me 4x. 2 times 5 is 10, all over 10. 3 times 5 is 15. 5 times 1 is 5, all over 10. And if I wanted to get a common denominator on the right side of the equation, you definitely could. Just to have them all out of tenths, that might be helpful. So you can pull the same trick if you wanted to. Make this one multiply by 5. This would be negative 5x plus 7 times 5, which is 35 all over 10. And then on the left side, since we do have a common denominator of 10, we can go ahead and perform the subtraction. Now, one thing to be very careful about is that the subtraction is happening to the 15 and to the 5. So one thing I kind of like to do is do that change of sign kind of early on. So I'm going to carry down the 4x plus 10. This will be minus 15x, and then minus 5 all over 10. So I could have done, 4 minus 15, right? And then that will get us negative 11. 10 minus 5 gets you 5. So I could perform the operation, but I have found that it's so easy to make mistakes with that negative and forget, say, to do the minus 5 piece of it, that I think it's kind of easier to just do the negative and then worry about combining numbers later. So now that I have it all written out, 4 minus 15, there's our negative 11x. 10 minus 5 is 5 all over 10. My other side of the equation is already done, so we can just carry him down. And this gets us to the point where we need to decide what to do with those tenths. So one thing I could do is I could treat this like a proportion and cross multiply. I could definitely do that. Another option I could do too is pulling that same fraction trick where you multiply both sides by the denominator of your fraction, right? And then that's going to cancel out both of the denominators of 10 for us. So really this is negative 11x plus 5 equals negative 5 plus 35. Negative 5x plus 35. Now in this one I showed the work for the common denominators because it is important to do that. Sometimes you really do need to get a common denominator to add and subtract fractions. If you were wondering though why at the very start of the problem I didn't just multiply by 10 on both sides of the equation, that would then get rid of our denominators for 2 and the 5 and the other value of 2, we could have done that as well, right? So there are multiple methods when you're solving equations, and I think that can be the part that trips people up at times. So just kind of acknowledge that you may have done it a slightly different way. In the end, if you end up getting the same answer result, that's fine. It just means you might have taken a slightly different path. So from this equation, I need to move all my x's together. So I could either add the 5x to the left or add the 11x and move it to the right side of the equation. Again, we're just using inverse operations, right? The opposite of the subtraction is addition. And why I chose to do the 11 is so that way my coefficient for x would be positive. 11 minus 5 is a positive 6. And I like that. So that's why I set it up that way. We could do the same thing with 35 and 5. Actually, I'll just carry it down and do it as a separate step. If you're good at equation solving, you can kind of do more movement in one step if you wanted, but here I'll take my time. So now that I have the 6x by itself, that means I want to move the 35. So the opposite or inverse operation is subtraction. So 5 minus 35 gets me negative 30 equals 6x. There is multiplication occurring between our 6 and our x. So the opposite would be dividing by 6 to get x all by itself. So negative 30 divided by 6 is negative 5. So one thing that we can do with that negative 5 for an equation that we can't do for an expression is we can check it. We can plug it back in and see if it balances our equation. So I might want to do that here just because we had quite a few operations occurring. It is very possible that we made a mistake, and we want to know that before we turn in our final exam. So what I would do, one way I could quickly check this is I could go into my calculator. Let's clear that out. And I'm going to type in each side of my equation and see what value I get. So I'm going to work with the left-hand side to start. So we do have multiple operations happening in the numerator, so you want to make sure that you group that inside a set of parentheses. So 5 times our negative 5. Be aware you want to use the negative key, not the subtraction key. Very different when you're dealing with negatives in this case. Plus 5. Close it in parentheses, divide by 5. And then minus, same sort of situation. I have multiple operations in my numerator, so group those in parentheses. 3 times my negative 5, added by 1, closing my parentheses, and then divide by 2. So here I have to be very careful in how I type things in on my calculator, because it doesn't show what's in the numerator and what's in the denominator. Some of the newer calculators actually have some buttons that allow you to format it just like you see it here, with stuff being on the top of the fraction and stuff being on the bottom. So I got my 6 for the left-hand side of my equation. Now I got to try the right-hand side. So I have minus already, and then there's a second negative happening for the negative 5. So there's a double negative. We're ultimately going to get a positive number there. Plus 7. Here's my numerator, divide by 2, and we also get a 6. So since both the left and right-hand side are 6 values of 6, we know that our value of negative 5 for x is the solution. That the only way the left and right-hand side could be equivalent is if we had found the correct x value. Problem 9 comes from section 7.3, and this question actually deals with unit price. So unit price is where we're going to take the price for our item and divide by the quantity. And the quantity could change depending upon what item you're talking about. If I'm talking about boxes of Kleenex, then it's going to be for each box of Kleenex that I buy, right? Sometimes you can buy them just one package, or in a bigger pack that has 3 or 4 boxes, or the really big bulk size ones that come with like 24 boxes. So it could be per box, it could be per ounce, right? Very typical way of measuring them is units is fluid ounces or weight ounces. So it could be set up that way. In this case, we're talking about pizza, so we'll look at what that looks like in a second here. So Domino's Pizza sells their cheese pizzas in a variety of sizes. A small 10-inch pizza costs $5.99, a medium 12-inch pizza costs $7.99, and a large 14-inch pizza costs $9.99. We want to calculate the unit price for each size of pizza, and that will help us determine which one is the best buy. Now this one is interesting because it's actually going to include some information from our geometry unit, that when we talk about unit price, the inch size of pizza is not necessarily all the pizza that you buy. When you buy a pizza, you're buying the whole area of that circular pizza, not just the distance across that they're giving us here. So they gave us the diameter, but that's not going to be an accurate way to measure our unit price. What we need to calculate is the area. What is the price I'm paying for the area of pizza that I'm going to be eating? So we need to calculate the area of our pizzas to actually get these done correctly. So I'm going to calculate the area of the 10-inch pizza. Then we'll calculate the area of the next size, which was 12-inch, and then we'll do area of the 14-inch. So this one had a little extra step to it in that we need to calculate the areas. If it was set up differently, if they weren't talking about pizza, if they were talking about, say, bottles of soda, then you wouldn't have to do that extra step. They would tell you the, say, fluid ounce amount or liter amount for your soda. This one, because we are talking about pizza, we do need to involve some geometry. So area of a pizza is circular in shape, so really I'm calculating area of a circle, which is pi r squared, and we're going to plug in the different radius measurements when we calculate these. So these are all involving the same formula. So for a 10-inch pizza, 10 inches is the distance across, what we call the diameter. Our radius is actually half of that. So half of 10, that's going to be 5 inches. When I square it, that is 25. and I just haven't calculated the measurement with pi just yet. I'll calculate that in one go when we get down to our unit price here in a second. So that's just to avoid having to round stuff too early. So you never want to round answers till you get to the very end. So that's what we're doing here. And then for a 12-inch pizza, half of our diameter would be 6 inches for the radius. 6 squared is 36. Our next piece for the 14-inch pizza, half of our diameter would be 7 for our radius. So 7 squared is 49 pi. And now we're going to go ahead and calculate the unit price. So remember, unit price is your price divided by quantity. So for the 10-inch pizza, our price was $5.99 divided by our area, 25 pi. For our next pizza, and we'll get a decimal number here, and that's why it says round to 4 decimal places, because sometimes it's really hard to tell the difference between unit prices if you don't go to enough decimal places. So actually, let me do this one right now. So in my calculator, how I would type that in is I would type in my price, 5.99, divided by, and because I have two values, I have 25 and pi, I definitely want to put those in parentheses for our denominator. And when you use pi, use the pi key. It's way more exact than any 3.14. So there's my decimal, 0.0763. All right, so again, keep in mind rounding rules. When I go to 4 places after my decimal point, the 6 is going to round up my 2 and make it a 3. So there's our first unit price. This was for the 10-inch one. And this is essentially price per square inch of pizza. That's what we calculated. We'll do the same thing for the next size. So the price was $7.99 divided by the area of my pizza, 36 pi. So same sort of deal, we'll very carefully type this into our calculator, $7.99 divided by parentheses, 36 pi. And that'd be 0.0706. And this was how much it cost per square inch of pizza for the 12-inch size. And then the last pizza cost $9.99, and the area was 49 pi. So 9.99 divided by 49 pi, 0.0649. So again, looking back, where did I get the 9 from? I went to 4 decimal places. That landed at my 8. If I look one more digit past that, it's a 9, so that's going to round ours up. And that would be the cost for the 14-inch pizza. Okay, so we have our unit prices. And we can definitely see when we compare those, the biggest number is the first one, the 10-inch pizza. So that would be overall the most expensive per square inch of pizza. The middle one, or the next highest one, was the 12-inch pizza. So that was definitely pretty significantly cheaper. But still, our best buy was the largest one. That was the cheapest price per square inch. So that's going to be the best pizza buy for us. So the large pizza is the best buy. At 0.0649 per square inch of pizza. Problem 10 comes from section 7.3, which is where we looked at solving proportions. So a nurse is asked to administer 200 milligrams of fluticasone, some sort of drug, to a patient. There is a stock solution that provides 40 milligrams of the drug per milliliter. We want to know how much of the solution should be given to the patient. So in a proportion, you're relating 4 measurements. So we have some relationship between milligrams and milliliters that we want to maintain the same ratio or relationship between those two values. So we want to know for 200 milligrams what that is in milliliters. So that's our unknown piece. You could call that some sort of variable like x. And that's based off of the relationship that there's 400 milligrams per milliliter. Now you may be wondering, well, how many milliliters is that? When they say per, it's an implied 1. So in 1 milliliter, there's the 40 milligrams of the drug. So one key thing to know about proportions is whatever your setup is on one side of your equation, the fractional setup, you want to make sure that that setup is maintained in the same order on the right side. So units can help us with that. So if you notice I wrote milligrams and milliliters, that's to make sure that I set them up both the same way. So milligrams on top, milliliters on the bottom. You could have done yours differently. Milliliters on top, milligrams on the bottom. It would be the same thing. Now that we have it set up, we can cross multiply. So 40 times x and 1 times 200, which is 200. And then we'll solve that equation. So to undo the multiplication by 40, we can divide by 40. That will isolate the x. 200 divided by 40 is 5. And we do want units. We're talking about 5 something. Here my labeling can save me. This is 5 milliliters of our drug. Problem 11 comes from section 7.4. And 7.4 is where we talked about solving inequalities. So here we have a word problem inequality that we want to write an inequality statement and then solve it. So Jane needs to rent a large outdoor tent for her wedding. Tents for Rent charges $25 per hour for their tents with a $100 delivery charge. A through Z Rentals charges $40 per hour for their rental tents and a $150 delivery charge. After how many hours will renting the tent from Tent for Rent cost more than renting it from A through Z Rentals? So here they definitely gave us a lot of information, and so it would be helpful for us to read through the problem once, just see what's going on, and then pull out that key bit, all the key bits of information, and organize it. So Tent for Rent, and organize kind of on one side here. They charge $25 per hour and a $100 delivery. A through Z charges $20 per hour and costs $150 for delivery. And we in particular are interested in how many hours, right? So that's what we're going to be solving for. Tent for Rent will cost more. So for Tent for Rent to cost more, we want the total amount that we're being charged to be greater. So there's our inequality. The Tent for Rent side is going to be greater than the A through Z. Now, we need to build an equation. All the equations that we dealt with in our course were linear equations. Linear equations have this format, y equals mx plus b. M is the slope. That is how our x and y values are changing relative to each other. And typically you'll see that in a word problem with something like an amount per something else. So when they say $25 per hour, that's a hint that that's my slope value. And then your B, that's your y-intercept or initial value. That's kind of what you're starting at, which is then increasing. So for us, that would be our delivery charge. You're going to have to pay the delivery charge no matter what. So that's like our initial value. So following mx plus b, this side would be 25m times x plus our b, which is 100. And the A through Z rental would be 20 times x plus 150. So I just use the mx plus b and acknowledging that the amount per hour was our slope and that the delivery charge was our y-intercept. So there is my equation for part A. In part B, we'll go ahead and solve it. Now, solving equations is very, very similar, or sorry, solving inequalities is very, very similar to solving equations. The ideas of isolating your variable and doing opposite operations to move terms around all work the same way. So if I want to get x by itself, I could move this 20x by subtracting from both sides. So 25 minus 20 leaves me with 5x plus 100. Now the key thing here is there's no equal sign. So what would be playing the role of our equal sign, that's our inequality symbol. And we got to make sure that we keep track of that guy, that we continue using that inequality symbol on each step of our work. Then I want to move the 100 to get the x term by itself. So I'll subtract it. I'm left with 5x is greater than 50. And then we divide to undo our multiplication by 5. So we end up getting x is greater than 10. So what does that mean for us? Well, we were figuring out when tent for rent would be more expensive. So tent for rent is more expensive when x is greater than 10. So x is our hours here. So if you are renting it for more than 10 hours, or after 10 hours, that's when it's more expensive. So we want to write that in a sentence to capture that information. So tent for rent will cost more than A through Z rentals after 10 hours. Problem 12 comes from section 7.5, and this is where we looked at scientific notation. And so here we have our numbers written in the standard notation that we usually see for numbers, but we want to convert them into the scientific notation. And the trick here is really just moving our decimal point. So I'm going to move my decimal point however many places I need to, so that where I leave my decimal, the value is between 1 and 10. So here I'd have to move it to create 4.65, that's between 1 and 10. And I had to move it 1, 2, 3, 4 places to the left. So that means I'm going to have a power of 4 on my 10. Now a common kind of mistake when it comes to scientific notation is the sign on your power. Should it be a positive power or a negative power? And this is how I remember which, that if you have a large quantity, like this is a large quantity, it's 46,500, that means you have a positive power. When you see a very small decimal like we see in B, that's where you're going to have a negative power occurring. So positive power means it's a large number, say thousands or millions and so on. Negative power means you have a very small decimal, so something like this with a bunch of leading zeros. So there's my value written in the scientific notation, so 4.65 times, we usually use that x symbol for times when we're dealing with scientific notation, 10 to the power of 4. Now B, Same idea, I want to move my decimal point however many places until I get a value between 1 and 10. So 9.9 is between 1 and 10. Now how many times did I have to move it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places to the right here. So the 10 places I would include. Now remember the signage though, since this was a very small number, that means our power is negative. So our final answer would be 9.9 times 10 to the negative 10. (13) is also from section 7.5, and it's also involving scientific notation. But this problem involves coming from the scientific notation and rewriting that in our standard numerical notation. So these are in the standard, scientific form, and we want to write them in standard form. So I'm going to first start by rewriting the number out in front, 1.52. And then we're going to move our decimal point, whatever power we see here. So I see a -2. That means I'm going to move it 2 places. Now the issue is which direction. Do I move it 2 to the left or 2 to the right? So one trick you can use is what I mentioned in the previous problem, which is acknowledging the sort of number you need to create. This negative power means I want to create a small number. So moving it to the right won't do that. It'll make it a big number. It'll make it 152. So to make it small, I need to move it to the left. That would create the small decimal that we were expecting. So 0.0152, that's the number we want. B, we're going to do the same thing. Take 7.51. We want to move it 6 places. We see a positive power on our 10. That means we want a big number. So moving it to the left would make it a small number. Nope, we don't want to do that. We want to move it to the right then to make it a big number. So I'm going to move it 6 places. 1, 2, 3, 4, 5, 6. There's a whole bunch of blank space here. For each of those blank spaces, you're writing a 0. So 7, 5, 1, followed by 4 zeros. And then you may want to add every third place is your comma. So this is 7,510,000. Problem 14 comes from section 8.2. This is where we looked at linear equations. In particular, we looked at slope. So we have a graph given here that represents the percent of wireless-only households in the United States for the years 2007 through 2012. We want to use the ordered pairs that are given on our graph to find the slope of the line to the nearest tenth. So normally a slope is a fraction, but here we want to round it as a decimal for our answer because that's going to be a little bit more meaningful for this particular problem. So they gave us our coordinates here. I don't have to find those on the graph, thankfully, but I do need to calculate my slope. So we need our slope formula, which is this guy right here. And anytime you're using a formula, we did this a lot for geometry where you write down the formula before you plug in numbers. However, that holds true for algebraic formulas too. You want to write down the formula so the person reading your work knows why you did all those operations before you plug in your numbers. So here, it doesn't matter which point I label as the first or the second. In the end result, our slope will give you the same answer regardless of how you picked it. So let's say my second point was the one from 2012. So the value was 38 there, minus my other value, which was 16, and 2012 minus 2007. So I would subtract each part separately before we divide. So 38 minus 16 is 22. 2012 minus 2007 is 5. Now remember, we want our answer rounded to the nearest tenth, so that is 4.4. Now why we wanted the decimal is for perhaps interpreting it, that it makes more sense to write it in that decimal form. So your slope, another way we can think of slope is rise over run. So graphically, you know, it's how far I need to travel up or down on my graph vertically, and that's compared to how I need to move left and right or on the run. So we have to rise a certain amount and run a certain amount, And that's what we can see for our 4.4 here. We can think of that as 4.4 over 1. So I need to go up 4.4% for every one value on my x, which is years, for every one year. So that's how we can interpret this. Your slope is write it as a fraction and then figure out what each value represents. So the 4.4 is the percentage increase for us. We went up 4.4% in our wireless only households per 1, which was 1 unit on our x's, which was the year. So now I just need to write that in a sentence. So the amount of wireless only households increased 4.4% each year. So there's a couple keywords that we want to make sure that we've included here. So one is our comparison, right? The rise versus the run, right? It was 4.4% for each 1 year. The other keyword was the increased piece, that our slope was positive, so that's an increased behavior. If you had a negative slope, that's a decreased behavior. So we do want to have that keyword, the increased or the decreased. Problem 15 comes from section 8.3. This was again where we looked at linear equations, and in particular writing out our full linear equation in, say, slope-intercept or point-slope form or one of our other formats for a linear equation. This problem says Emily regularly uses a shipping company for her work. The company charges a service fee in addition to a charge for each ounce the package weighs. For a 16-ounce package, the shipment charge was $8.40, and a 70-ounce package costs $30. And this one is set up in multiple parts to help guide us through the problem. So A, we want to know how much the shipping company charges per ounce of weight. That per is a hint we're going to find slope. Part B, we want to know the service fee. Fees are usually your y-intercept. Then we're going to use those two to write our linear equation in slope-intercept form. Y equals mx plus b. Then with that equation, we'll go ahead and graph it. So when you have a multi-part question, a good idea would be to first read through all the parts, know what you're working towards, because sometimes that'll give you a hint if you weren't sure. So if I wasn't quite sure what I was doing in parts A or B, looking and seeing that I'm going to eventually generate a linear equation and then graph it in parts C and D would help me recognize that I'm finding the slope and the y-intercept. So part A, how much does this shipping company charge per ounce of weight? That's our slope. So I can write my slope formula that we used in our last problem. And if you notice, they did not give us coordinates written out explicitly, but they are there. So they told us for 16 ounces of weight, the charge was $8.40. That's one coordinate. And for a 70-ounce package, the cost was $30. And if you were wondering how I knew to set it up that way, that 16 would be x and 840 would be y, they're telling us that in our setup. They said charge per ounce. So slope is y compared to x. So y is the charge, x is the ounces. Another way to think of it too is that your input value x is always some value that you can decide upon, like how much my package weighs. The y value, or your output, that's going to be a value that you can only determine knowing your input, which would be like our charge. I only know how much money I need to pay after I know what the package weighs. So now that I have my coordinates, we can plug it into our equation here. So whichever way you want to label it, I'll call this one x1, y1, x2, y2. So we're going to do 30 minus 840 on the top and 70 minus 16 on the bottom. So we have to subtract before we can divide. 30 minus 80.4 is 21.60. 70 minus 16 is 54. And then we'll go ahead and divide those. So here I could leave it in the fractional form. or get the decimal. The decimal's fine here. It's 0.4. That's going to be helpful in writing out what our cost per weight is. So this is my cost, right? This is our slope. So if I put this over 1, this is the amount of money per 1 ounce, right? Remember, because X was the ounces, Y was the price in dollars. So we know our charge is 40 cents per ounce. Part B, we want our service charge. That's the B, or service fee rather. That's our y-intercept. So I can use my slope-intercept form, y equals mx plus b, and plug in one of our points to help reveal the b. And it doesn't matter which one we pick. So I'm going to just pick 16 and 840. So my y value was 840. My slope was that 40 cents. And the x was the weight of 16 ounces. The only part of this equation I don't know is the b. And that's what we're going to go ahead and solve for here in a second. So I'll multiply 16 times 0.4, that's 6.4. And then to get b by itself, so I can find the value of b, we need to subtract off the 6.4. And I end up getting 2. So our y-intercept, which here is represented by our service fee, is $2. So there's a $2 fee. So we'll pull the information from part A and from part B to generate our linear equation. So the linear equation is y equals mx plus b. That's the slope-intercept form. I'm going to leave x and y alone. So y is that charge, x is the weight. The slope we found was 0.4, and the y-intercept b was 2. So I'm just going to plug in the m and the b, and that will give us our equation. And now we need to graph it. So my equation was 0.4x plus 2. And in terms of graphing, although the 0.4 is helpful in understanding our slope for this problem, it's not very helpful for graphing. So what I'm actually going to do is change my 0.4 into its fractional form. So the fractional form is 2/5. That just makes it a lot easier to graph. So when it comes to slope, you want the fraction to help you in graphing. And that's because when I have an y equals mx plus b, I can graph the y-intercept point to start, and then use my slope to find additional points on my line by using the rise and the run. So before I do that, if you notice, my graph does not have any scale labeled. And we definitely want to label that. So I can kind of look at my equation. I can see my slope is 2/5. That's not too crazy. My y-intercept is 2, that's not too crazy. So I shouldn't be worried about very large numbers or very strange small numbers that we'd really need to adjust our scale for. So counting by 1 should be fine. And I, in particular, like to label my graphs at every other tick mark. I'm still counting by 1s, but I'm just labeling the even values. And that's just to make sure my graph doesn't get too cluttered. It's really easy to clutter it up with a bunch of labels if you count each and every tick mark. So whatever scale you pick and however you choose to label it, every tick mark or say every other, oops, or maybe every third or whatever your preference is, do make sure that you label going in all 4 directions. You want to make sure this graph is completely labeled. There we go. All my scale is labeled. Now we can go ahead and graph. So I'm going to start with my y-intercept point 0.2. Then I'm going to count off my rise and run. So the rise is positive. That means I'm going to go up 2 units. And then my run is positive. That's movement to the right 5. So from my y-intercept point, I'm going to go up 2, right 1, 2, 3, 4, 5. There's another point on my line. And I can keep doing that as many times as I want to. So if you have a straight edge or a ruler, then it's pretty easy to draw a straight line. I'm not very good at drawing straight lines in general, so I try to get as many points as I can. So I got all the values to the right. If I wanted to also get some values to the left, I can just reverse my directions. Instead of going up, I'll go down 2 units. Instead of going right, I'll go to the left. 1, 2, 3, 4, 5. So there's another point down 2. 1, 2, 3, 4, 5 to the left. And once I feel like I've had enough points on my line that I can be confident to draw a fairly accurate line. Go ahead and draw it, and then make sure you include the double-headed arrow on each side to show that our line will continue going on in each direction. Problem 16 is from section 9.3. That was our triangle section in our geometry unit. And so we can definitely see that. We have a triangle in our picture. And so there's lots of things that we can do with triangles. So we'll figure out which rule or property for triangles we want to use here. So a utility pole fell over in a recent storm. The pole broke 3 feet from its base, and its top is resting on the ground 20 feet away. What is the original height of the utility pole? Round your answer to the nearest foot. So we can see here they labeled the information in our diagram. So here's the height of our pole where it broke. Right now it's laying on the ground. The tip of it is 20 feet away. And we want to figure out the height of the original pole. Well, I know this piece of it's 3 inches, so what's missing is the part that's kind of lying slanted here. We need to figure out the other part of the length of the pole. Well, the good news is we have a very recognizable shape here. We have a right-angled triangle. And when you're interested in the 3 side lengths in a right-angled triangle, that's Pythagorean's theorem. A squared plus b squared equals c squared. So the missing length for us is the c, and the other 2 lengths could be a or b, it doesn't matter. So I'm going to write down my formula. That's important. To get full points, you got to write it in before I plug in my numbers. And then we'll continue calculating it. So 3 squared is 9. 20 squared gets me 400. I need to add those up. That's 409 equals c squared. But I want c by itself, no power 2. So to undo the power 2, you're going to square root it. So I'm calculating the square root of 409. You need to make sure whatever calculator you're using, you know how to type that in. So sometimes that may be a secondary menu option. So second square root, 409. There's my value. Now they said to round it to the nearest foot. So here, that's like the nearest whole number. So the 0.2 is not enough to round up my answer, so it's going to be 20. And I might want to throw my approximate symbol just so that I remind myself I did round that. And before I circle it and say that I'm done, I am not done because that's only the section that's kind of lying at a slant. We want to know the height of the original pole. So I need to add 20 feet to the other part of the pole, which was the 3-foot section that is where it got broken. So 20 plus 3, the actual length of our entire pole was 23 feet. So we did need to use Pythagorean's theorem, but we also had to include the 3 feet as well. (17) also comes from our section 9.3, the triangle section. Here we have a tourist that's 200 feet away from the Statue of Liberty looking at the top through a pair of binoculars. And we want to know at what angle must the tourist look up to see the top of the statue. So they gave us a triangle picture here. We can see we're interested in finding this angle measurement. Our tourist is 200 feet away from our Statue of Liberty. The Statue of Liberty is 305 feet tall. And all objects, kind of like our last example, if they're standing straight up, you can assume that they're perpendicular. So we have a right-angled triangle. We're interested in the relationship between an angle measurement and a side length. So when you're relating angles and sides in a right triangle, that's your trigonometric ratios. Remember our 3 trigonometric ratios were sine, cosine, and tangent. And one way we could remember the setup was through SOHCAHTOA. So your sine of your angle is the opposite divided by hypotenuse, cosine is adjacent divided by hypotenuse, and tangent is opposite over adjacent. So to decide which of the 3 we need to use, we can label our triangle. So I always like to start with opposite. So from your angle that you're interested in or that's given, the side across from that is your opposite side. The side across from 90, or your longest side, is the hypotenuse. And then the third side, whatever's left over, is the adjacent. So here, the numbers that are given are the opposite and the adjacent side. So that means I need to use the trigonometric ratio that uses the opposite and adjacent, which is tangent. So TOA helps us with the setup. Tangent of your angle measure is the opposite side divided by the adjacent side. Now here, I don't know my angle A. That's the x for us that we need to find. The opposite side is 305. The adjacent side is 200. So this one is interesting because of where my variable is. My variable is stuck inside of tangent. And so to undo the tangent and free up my variable, so it's all by itself, I need to do the opposite of tangent, which is called the tangent inverse. Right? It's a little tangent with a -1 on there. So when I apply the tangent inverse, it's going to cancel out my tangent. So x is by itself. And what I need to calculate is the tangent inverse of 305 over 200. Now I will need to type that into my calculator. Before I do, I want to check which mode I'm in. So graphing calculators in particular are very bad at not being set in the correct mode at times. Your other types of calculators, like the scientifics, usually default to the degree mode, and so you're fine. Graphing calculators usually don't. So here I clicked my mode button, and you can see I am not in degree, I'm in radian. So I need to arrow down and make sure that I enter the degree, that the degree is now highlighted. Once it's highlighted, I can exit out. And now when I do my tangent inverse, it will calculate it in degrees for us, which is what we need. So make sure whatever calculator you're using, you're familiar enough with it, and you know the settings well enough to make sure that you are in that degree mode. So when I type in my tangent inverse, I get my 56 points, and if you're not sure what to round to, they didn't tell us any information on how many decimal places, then you're going to go to the default instructions on the exam, which is to 2 decimal places. So 745 would round up to 0.75. So this is about 56.75, and our angles are measured in units of degrees. So we want to make sure we have that degree symbol on our answer. Problem 18 is also from our triangle section, section 9.3. This time we have a contractor that's installing a handicap accessible ramp onto the side of a building. The ramp must reach the top of a 4-foot entryway to the building and cannot exceed a 15-degree grade for safety reasons. What is the length of the ramp? So here we can see a picture. Here's our 4-foot length that we need our ramp to go up to on the side of the building. The grade is our degree, right? The angle that is formed here. And we want to know the length of the ramp. So what we want to find is this measurement up here, right? The part that people would actually walk on. So here I have a right angle triangle. We want to relate side lengths with angle measurements. So that is our trigonometric ratios. That's SOHCAHTOA. And we need to make sure we pick the right one. So I'm going to go ahead and label this. Across from my 15-degree angle, 4 is our opposite side. The unknown piece is our hypotenuse, and the adjacent side is the last one. So I want to use opposite and hypotenuse. So opposite and hypotenuse is the SOH or sine. So sine of your angle is equal to the opposite side of your triangle divided by the hypotenuse. And my angle was 15 degrees, so I'm going to replace the 15 degrees in there. The opposite side measurement was 4 feet. And the hypotenuse is what's unknown for us. So we can call that x or some other variable. So now that I have my equation written, we want to go ahead and solve for x. And this is a particularly tricky one because x is in the bottom of my fraction. So don't let that get you too tripped up. We can take the same algebraic trick that we've used in the past, which is to multiply your denominator. If I multiply x, it'll get x out of the denominator for me. And now it'll just be multiplying by the sine of 15 degrees. And now I have to get x by itself. I don't want the sine of 15 there. So I can undo my multiplication by dividing the sine of 15 degrees. So our variable x is 4 divided by the sine of 15 degrees. That's the exact value. But we need to type it into the calculator to get our decimal value. So 15 divided by sine, oh sorry, other way. 4 divided by sine 15 degrees. And we get 15.45. They did not give us any rounding instructions on the question, so that means we're going to go to the defaulted 2 decimal places that are the instructions given on the start of the exam. So 15.45 is our rounded result. And this does involve units. Make sure you include them. I'm going to be using the same units as the other side length in my triangle, so this is in feet. Problem 19 comes from section 9.4, which was our perimeter and area unit. So here we can kind of look at our diagram and see that we're going to have a trapezoid. And I think they also explain that in our problem as well. So there are all these different formulas for perimeters and areas of our shapes. So from the section 9.4 notes, I definitely want to make sure I copy down those key formulas for perimeter and area onto my exam reference sheets. So this one says you're mowing lawns to make extra money over the summer. A local company hires you to mow their lawn, which is in the shape of a trapezoid. The lengths of the bases of the lawn are 60 feet and 80 feet, and the height is 30 feet. You charge 2 cents per square foot. How much will you earn mowing the lawn? So here we need to find the area of our lawn in order to figure out our charge, right? Our charge is 2 cents per square foot. So I need to figure out how large this lawn is in terms of square feet. Square feet is a unit in area. So that's a hint that we want the area here. So area of a trapezoid, I would look that up on my formula chart from my notes. That is 1/2 times the height of my trapezoid multiplied by the sum of the bases, b1 plus base 2 in parentheses. So the key thing when you're dealing with formulas, write down your formula. That does count as a step of work on your exam, and if you leave it off, you lose points. You don't want to lose points because you forgot to write down your formula. And then I'm going to plug in my numbers. So I'm going to plug in my height, that's the 30 feet, and then our bases are the 60 and 80. So I need to follow PEMDAS here. I'm going to add the 60 and the 80. That gets me 140. And then I'm going to go ahead and do our 1/2 times 30 times 140. You can multiply all three all together in your calculator. You could do the 30 times 140 first and then do the 1/2. Your final answer though is 2,100 square feet. So that would be a key number that I'd want to see on your exam, right? We need that area before we can calculate our pay. So now I'm going to take my area and I'm going to convert that into a measurement in terms of pay. So this is an instance, since you want to change feet into dollars, you can use dimensional analysis. So I'm going to write my area as a value over 1, just so it's a fraction. And then my rate is 2 cents per square foot. So 1 square foot is equivalent to 2 cents in our wage. So how dimensional analysis works is we want to line up our units so the units we don't want anymore are going to cancel. So my square feet would cancel and then I'd be left with the units I do want to keep, which is the $2. So ultimately I need to multiply these. 2,100 times the 2 cents is going to give me $42. So make sure whatever you did here, if you use dimensional analysis or just regular multiplication, that you've shown your work and that you have your units on your answer, that this is a measurement in dollars. Problem 20 also comes from section 9.4, which is our area and perimeter unit. So again, I want to make sure all of my perimeter and area formulas from this note section are on my exam reference sheets. This one involves pizza. We have 3 pizzas given, different diameters, 8 inches, 12 inches, and 16 inches, and we want to figure out which ones would produce the largest slices. So to figure out the largest slice, I need to find the area. So I'm going to calculate the area of each of these. So part A is the 8-inch pizza. So area of a circle is pi r squared. The distance across my pizza, the diameter is 8. The radius is half that. So the radius is 4 here. So I'm going to plug 4 in as the radius in my formula. 4 squared is 16 times pi. And before I calculate what that area is, there's more math to happen later. We need to cut this into the 6 slices. So I don't want to calculate my answer with pi and then get a decimal and then later round it. So a good tip when you're dealing with things in terms of pi, wait till the very last step to actually calculate your pi and get the decimal. So there's my area written exactly. To figure out the amount per slice, I'm going to take my area and divide by the number of slices. We're cutting it into 6 slices, and that will be what I actually type into my calculator now to get the final answer. So I just want to be careful because 16 and pi are both in the numerator. You want to group those in parentheses. So I'm going to do 16 and then use your pi symbol. Don't use 3.14 because the pi symbol is going to be way more exact. It's also easier to type in too. So 16 pi in parentheses divided by 6. And there's our value. And they didn't tell us what to round to in this problem, so we're going to round to the default way of rounding, which is 2 decimal places. So 8.38 would be our value here. And we do want units, since we were talking about inches, and we calculated the area. The area is square inches. And we divide by the number of slices, so this is per slice. So you get 8.38 square inches of pizza per slice. Now for B, we're going to move on to the 12-inch pizza. So this one's going to be essentially the same thing. We're calculating area of a circle, which is pi r squared. The radius is going to be half of my 12, so that's 6 inches. 6 squared will get you 36 pi for the area, and then we need to divide by the number of slices. So there are 8 congruent slices this time, and now I will calculate that. 36 pi divided by 8, 14.14 if we round it to 2 places. And this would be square inches per slice. So you pizza lovers out there, right? Clearly more pizza per slice on that one. Right? That's pretty nice. Make sure you go for the bigger size, huh? And then we'll do the 16-inch. So 16-inch here. Half of that will be our radius. First calculate the area of the circle, pi r squared. Plugging in the radius, which we said was 8. Squaring 8 is 64 times pi. And then I need to divide by the number of slices. This time there are 10 slices. 64 pi divided by 10. Oh man, look at that. 20 square inches of pizza. That's pretty awesome. So 20.11 actually for the big one. So square inches per slice. Definitely kind of motivates you for that bigger size pizza, huh? Problem 21 comes from section 9.5, which was our surface area and volume unit. So that section of notes had a formula chart with different three-dimensional shapes that gave our volume formulas and our surface area formulas, both total surface area and lateral surface area. So as I prepare my formula sheets or the reference sheets for the exam, you definitely want to include all those formulas. Unless you know them off the top of your head, you want to definitely make sure they're included on your reference sheet. So here we have a contractor that's building a set of concrete stairs as shown in the diagram below. All measurements are in inches on our diagram. We want to know how much concrete will be needed to make the stairs. So here I need to decide, am I talking about surface area right? Stuff on the exterior of my shape, right? Kind of all these surfaces that we would see on our shape, that's your surface area. Or volume, the stuff on the inside. So if I'm making these stairs out of concrete, that means I'm going to fill the entire shape that we see here with concrete. And that's volume. So I want to calculate volume here. And this is not a traditional shape that you would see on your formula sheet, so you may need to cut your shape. If I cut it right here, we can see we create kind of two rectangular prisms or boxes. And so the volume formula for a prism is the length times the width times the height. And I'll calculate that for each of these. And in fact, let me go ahead and label them. I'm going to call this one Prism 1 and Prism 2. So for Prism 1, the volume is the length times the width times the height. If I look very carefully at this, and this is where maybe looking at the top may be helpful, you can see this measurement here is 4. The width of it would be running this way. And so if you look down here, they say that's 4. So that's going to be maintained. This guy is also 4. And then the height is written here on the side. It's 5. So I need to multiply 4 times 5, which is 80. And my volume would be cubic inches, or inches cubed here. And then for the second prism, same formula, length times width times height. Again, looking at the top may help us with our measurements. So this one's 5 for the length. The width is that measurement of 4 that we saw on the right side. And then the height of it would be 2. So 5 times 4 times 2, that gets me 40 cubic inches. And so our total volume is going to be those two added together. So 80 plus 40, that gets me 120 cubic inches. Problem 22 also comes from section 9.5, which was our surface area in volume unit. So similar to what I mentioned on the last question, do make sure that your exam reference sheets have all the formulas that came from that note section for volume and surface area. This problem says the grain storage tank is in the shape of a cylinder covered by a half sphere as shown. The height of the cylinder is 50 feet and the diameter is 80 feet, and we want to find the total volume of the tank. So this one, again, kind of like our last example, it's not a typical three-dimensional shape, but we can make it from typical three-dimensional shapes. So I can think of this as a cylinder on the bottom and then half of a sphere on top here. So I need to calculate the volume of each of those separately, and then we'll go ahead and add them together. So the cylinder has a volume formula of pi r squared h. The sphere has a formula of 4/3 pi r cubed. And so what I need to do is write down my formulas before I plug in my numbers. So the radius is coming from the diameter here. So the full distance, the diameter is 80. Our radius would be half that, which would be 40 feet. And then the height is at 50 feet. So what I can do, because these both have pi, I can leave the pi alone and calculate my other values. So 40 squared I can calculate and then multiply that by 50, and that's 80,000 times pi. Now here, I don't want to calculate the value of pi just yet because that's going to give me a decimal, and we still have more work to do in our problem. So you don't want to calculate any decimals and do any rounding till the very end. And so we'll save that pi calculation until later in the problem for us. The sphere is 4/3 pi. We said our radius was 40 cubed. So this time I'm going to do 40 cubed and then multiply it by 4/3. If you want to see what that would look like in your calculator, I would type in my 4/3 inside parentheses just to be safe, and then times 40. You usually have to use that caret key or power key to get power 3. You notice we get a fraction, a decimal. We want to change that back into the fractional form. And this time it won't do it for me, and here's why. Because the number is so big, that my calculator is losing track of some decimal places at the end, and so it's not able to turn it back into a fraction. But this is in fact a fraction. How I could do it is, rather than relying on the calculator to do my division by 3, I can do that by myself later. So I can do the 40 cubed part and then multiply it by the 4. Right? This is also a fraction, it's like it's over 1. So you multiply the top of each fraction, so take this times 4. And that's going to be the top of my fraction out of 3. So we do get a very large numerator here, and that's why our calculator struggled to put it back in the fractional form when we had the decimal listed on the screen. So now I need to calculate the total volume. So I'm going to take the volume from the cylinder, which is the 80,000 pi, and I'm going to add it with half of my sphere, so half of the 265,000 over 3, wow, times pi. And if I'm careful, I could type this all in one go. The alternative is we could figure out what this 1/2 piece is. So this would end up being, oops, I lost my 6 somehow in there, 256,000 over 6, and then I could see if that reduces it all. So this over 6, and it's not, right? We're going to have a fractional piece of it. So since I'm kind of running into some nastiness in terms of my values, they're getting kind of big, we're already pretty much at our final answer. We could just very carefully type it into the calculator. So 80,000, there it is. Use your pi key, plus, I'm going to put my fraction in parentheses, 1/2, times 256,000 divided by 3. So if you notice I'm putting my fractions in parentheses, that's a good trick to make sure your calculator knows those are indeed fractions, times pi. And there is my answer. So what we'll go ahead and do now is write down our answer, and they didn't tell us what to round to, so we'll go ahead and round to 2 decimal places. So our answer would be approximately 385,368 point. Now here, if I go to 2 decimal places, my 8 needs to round up the 9, and it's already as high as it can go, so it's actually going to round this up to 0.70 because of that. And then my volume is measured in cubic feet here. Problem 23 comes from the section of notes, couple section of notes actually. It's combining section 10.1 and 10.2, which was counting the number of ways that something could occur, with 11.1, which was our basic probability unit. So a coffee shop sells hot and cold beverages in 3 sizes. The customers can choose from plain, chocolate, vanilla, and hazelnut flavorings. Part A asks how many different drink combinations can a customer order, and Part B is asking, assuming all drink order combinations are equally likely, what is the probability that a customer orders the largest cold coffee drink of any flavor? So here, for Part A, I could systematically write out all the different options. So if somebody orders a hot, small-sized plain coffee, a hot, small-sized chocolate coffee, and so on, but that's going to get pretty boring pretty quickly here. So we can use what's called the fundamental counting principle, which says that if you have all these different options that you need to select from, that you can multiply all of your different number of possibilities together to get the total number of options. So here we need to make 3 decisions: the temperature of my coffee, the size, and the flavor. So the temperature has 2 options, hot and cold. We have 3 size options. And for the flavors, I have plain, chocolate, vanilla, and hazelnut, which are 4 different flavorings. So we would just multiply those, 2 times 3 times 4, that means that there's 24 possible drink orders. Now part B is saying, assuming all of our drink orders are equally likely, what's the probability that a customer would come in and order the largest cold coffee drink? So I need to figure out how many coffee drinks would count as the largest cold one. So using the same fundamental counting principle, I'm going to look at the temperature. We specifically want it to be cold. We want to know the size. It must be specifically large. And the flavor, they did not specify the flavor. It could be any. So there's one temperature choice, I must pick cold. There's one size, I must be large, but there's 4 flavor options. So 1 times 1 times 4, that's 4 orders that would fit that description. So how probability works is you would do the number of desired outcomes. There's 4. Out of the total possible outcomes, there are 24. And we would divide that, and we want to typically write our answer either as a reduced fraction. This guy reduces down to 1/6, or as a decimal. So here I'd write my decimal to 2 decimal places. It's 0.17 if we round it, or as a percentage. So 0.17 is 17%. So you may be asked to represent it any of those 3 ways or all 3 ways. So be prepared to give your probability answer either as a reduced fraction, a decimal, or a percentage. Problem 24 comes from the combined notes section 11.2 and 11.3, which was the probability rules section where we talked about the complement probabilities, the probabilities involving or, so the probability of this or probability of that, the formula involved there, and our and type probabilities. If you want this event and a second event, how you calculate with the and formula the probabilities. So a bookstore has reviewed its receipts from last month and noted that for all 325 customers that made a purchase, 5 bought e-readers, 145 bought books, 250 bought magazines, and 75 bought both books and magazines. And we want to calculate a couple different things: the likelihood of a customer buying a book. That's part A. Part B is the likelihood that they bought a book or a magazine. I'm hearing that keyword "or" there. Part C, what is the likelihood a customer bought an e-reader and a book? So part A, we just want to know the probability that someone bought a book. So we can use all the different people that bought books, there was 145, out of the total. Now here, if you notice, they did tell us the total, it was 325. But if you add up the 5 and the 145 and the 250 and the 75, that's actually not 325. When I add all these up, I get 475. So what that's telling me is, you know, these 75 people that bought books and magazines, those are included in our 250 and the 145. That's why we're not getting the same total of 375. So that can happen, that you could have events that kind of fall in multiple categories, and so in that sense they are kind of included in both. So the total is the 325, not the 475. So kind of be aware there is that little added piece here. So I would take my fraction, reduce it, and hopefully you know how to reduce your fraction in whatever calculator that you're going to use on the exam. That's a very useful skill for using calculators. So on mine, how I would do that is I type in my fraction, 145 divided by 325. I get my answer as a decimal, and then know for your particular calculator what buttons you need to press to turn your decimal back into a fraction. And in your calculator, it'll always convert it back into a fraction in reduced form for us. So that is 29 out of 65. Now here they did not tell me how they wanted the answer written, so I'm going to cover all my bases. I'm going to write it as the fraction, the decimal, and the percent. So my fraction, or sorry, my decimal will round to 2 places, so this would round to 0.45. And that is 45%. Part B, we want to know the likelihood. When they say likelihood, they're just talking about probability. So the probability someone bought a book or a magazine. So, or type probabilities have a very specific formula. The formula is you would find the probability of the first item, so the probability of book. You'd add it with the probability of the second item, probability of a magazine. And then you do need to subtract off the probability of both occurring, that someone bought a book and a magazine. So for us, because they listed out all the different purchases, we can find these probabilities. The book probability is what we found earlier in Part A. It was the 145 out of 325. For magazines, there was 250 people that bought magazines out of the 325. And here we do have people that bought both, right? 75 people bought both books and magazines. Occasionally, that may not be an option. Your two events are what we call independent. There isn't any overlap in the two categories. So in that instance, this subtracted probability would be 0. You wouldn't have anything to subtract off. Here we actually do have something to subtract off. So these are all out of 325. So I can just perform the operations adding and subtracting across the top of my fraction since they have a common denominator. So 145 added with 250 minus 75 gets me 320 out of 325. And then similar to our last problem, I want to reduce that. You can definitely reduce it in your calculator because this is definitely a large fractional value, which is not the easiest thing to reduce by hand. So use your calculator and the appropriate keys to reduce it. 65/64. Oops, or 64 out of 65 rather. The decimal was 0.98 or 98%. Now part C, we want to find the likelihood, that's our probability, that a customer bought an e-reader and a book. So this is the AND type probability, which also has a specific formula, that you're going to find the probability of the first item, that someone bought an e-reader, and you're going to multiply it by the probability that someone bought a book. And sometimes when you're doing this AND type probability, the second probability you may have to adjust knowing that the first thing occurred. Now here we don't have to worry about that because someone buying an e-reader versus buying a book are independent events, right? If I go in and buy an e-reader, that doesn't necessarily affect my purchase of buying a book. And so we don't need to adjust our probabilities. There are instances where you do need to. So a classic example is drawing, say, items from a bag, right? If I took an item out of a bag and kept it, there are now fewer items in that bag for me to choose from on my second draw. So that's where the second probability would definitely be affected by our first action. So for our e-readers, there was 5 people that bought the e-readers out of our 325. And then when I multiply that times the number of people that bought a book, there was the 145 out of 325 that bought a book. So multiplication, we just multiply across the top. 5 times 145 is 725. Multiply the bottom, 325 times 325 is 105,625. That is a crazy big fraction. Definitely one I would likely want reduced in my calculator for me. So it reduces a little bit, it looks like here, to 29 out of 4,225. That would be as a decimal. Now here, if I go to 2 decimal places, we kind of run into trouble because they're both zeros. So in an instance like this, you may want to go a little bit further, maybe 3 decimal places, just so that we don't round up too much. So if I go to 3 decimal places, 0.007 would be kind of the better way to go. So it was 29 out of 4,225. and then our decimal was 0.007. Or, now here when I write it as a percentage and I move my decimal point 2 places, I still have a decimal. So this is a very small percentage. It's 0.7, right? It's less than 1%. That's super, super small. So not very likely that someone goes in and buys both those items. Problem 25 comes from section 11.5, which is our expected value section. So Bob regularly buys lottery tickets. Each ticket costs $2, but has prizes of $100, $500, and $20,000. The ticket lists the likelihood of winning each prize as follows. 2 out of 10,000 for the $100 prize, 1 out of 10,000 for the $50 prize, $500 prize, and 1 out of 100,000 for the $20,000 prize. How much money in winnings can Bob expect if he continues buying lottery tickets? So the expected value, one way to organize it very nicely is to make a table. So we make a table of all the different possible situations, what value we can expect from each situation, and the probability that that situation occurs. So Bob could win the $100 prize. That's one possibility. He could win the $500 prize. That's another possibility. He could win the $20,000 prize. Or he could not win anything. So you want to make sure that you've included all the different possibilities when you're making your table, and then we'll figure out our values. So let's say he won the $100 prize. He would win $100, but he had to pay $2 to play the game, to play the lottery, so he didn't get that back. He kind of lost those $2. So overall, he'd be getting $98. The probability of him getting one of those tickets, they said, was 2 out of 10,000. And what will be helpful here, because that's kind of a weird fraction, is the decimal may be helpful. So I want to calculate this exactly. 2 divided by 10,000 is 0.0002. So here the decimal is just going to be a little bit easier to work with than that big fraction. The second value is he could win $500. Now again, he has to pay $2 to get the ticket, so he's really only winning $498. The likelihood that he wins that prize is 1 out of 10,000. And the decimal there would be 0.0001. He could win the $20,000 prize. But again, he had to pay $2, so his actual winnings would be $19,998. And the likelihood he won that prize was 1 out of 100,000. And as a decimal, that would be 0, followed by 1, 2, 3, 4 zeros after the decimal point, and then a 1. Now for him not to win, that means he didn't win any money. He still paid $2, so he's actually down. He kind of lost those $2 that he paid for the ticket. Now here, they didn't talk about that probability, but we can calculate it using the complement. And so the complement is helpful when you know all the other events except one in your sample space. So I'm going to take 1 and subtract the probabilities that I do know, right? I know the probability from him winning the $100, that was the 2 out of the 10,000, or 0.0002. The probability of him winning the $500, that's 1 out of 10,000, or 0.0001. And the probability that he wins the 20,000, that's 1 out of 10,000, or 0.00001. So when I add up all those probabilities of him actually winning something, it's 0.00031. 1 taken away from that will give us the probability he doesn't win, which is 0.99969. And I've done absolutely no rounding here for all of these decimals, and that's important. We do not want to round any of our answers until the very end. That can very much throw off your answers for expected value, especially in this instance where the numbers are pretty big. Rounding my decimal places in any way will totally change my final answer, and we don't want to do that. So how do you calculate the expected winnings, or the expected value? Is you're going to take each of your values, you're going to multiply them by your probability for that particular event occurring, and then you're going to add them all together. So the first value was the $98. The likelihood that he won, the probability, was 0.0002. Then we're going to add that with the next event, which was the $500 win. He'd actually be getting the $498 back. The probability was 0.0001. And then the big prize, he'd actually be winning $19,998. The likelihood was 0.00001. And then the last case, which is he doesn't win, that means he goes down by $2, so I'm adding the value. It's still adding, but this time my value is negative, and the probability is 0.99969. So this one, we definitely want to be careful typing it in, especially with all those zeros there. As long as we're careful, we should be fine. So 98 times 0.0002. Oops. I guess I could use parentheses on this one instead of the multiplication sign. Okay, plus 498 times 0.0001 plus 19,998 times 0.0001, and then plus my -2. So you can either do plus the negative or use your minus key. Either one is fine. Times 0.99969. And what I end up getting is -1.73. So what does that mean in my situation? Well, we're talking about the expected value that Bob's going to get if he keeps playing this game over and over again. So in the long run, what would he expect to happen each time he plays this lottery? So we can see it's a negative number, so he's going to lose money. So Bob will lose and this is our amount, $1.73 each time he plays. Now, if you're wondering where that number came from, the idea is in the long run. So he may win a couple times as he plays, right? But in the long run, because there's such a high probability that he's not going to win anything, he's going to lose those $2 so many times over and over that even if he did win a prize, in the long run he's going to lose almost his whole amount, right? Just a little bit under $2. Problem 26 also comes from section 11.5, our expected value section. So this one says an appliance company sells a particular brand of washing machine for $650. 2% of the machines that are sold have shown to have a manufacturing defect that will require a $500 repair. Any defective machines reported to the company will be repaired at no cost to the customer that purchased the machine. What is the expected revenue that the company can expect each time they sell a washing machine? So similar to our last problem, a good way to start this problem is to organize it in our table. So we're going to look at all the different events that are possible, what value you get for each event, and the probability of each event. So the first event is I sell a machine and it has no defect. The other option is that it does have a defect. So as you create this table, you want to make sure you've included all the eventualities, right? Either it's got a defect or it doesn't. That'll cover all the possibilities. So if it doesn't have a defect, I'm looking at this from the perspective of the company and expected money. That's what revenue is, how much money they're going to make. So they're going to make $650 on that machine. And if it does have a defect, it's going to require a $500 repair that the company pays for. So they got $650. They need to subtract the $50 they're going to pay to get it repaired because of that defect. So really they're only making $150 on a machine like that. Now in terms of probability, they said 2% of the machines sold have the defect. So the probability of the defect is 2%. Now we want to write that as a decimal. Anytime you're involving percentages and you're doing math on them, you want to write them in the decimal form, not the percent form. So that's 0.02, that's our 2%. They didn't tell us the likelihood of it not having a defect, but that's okay. We can use our complement rule. And that says that when you've accounted for all the possibilities and there's only one missing, you can do 1 minus all the other probabilities that you found, and that'll figure out whatever's left over. So here, there's only 2 possibilities. So 1 minus the 2% is the other probability, which is 0.98 or 98%. So to find our expected revenue, our expected value, you're going to take each of your values, you're going to multiply them by their probabilities, and then you're going to add them all up. So here, my first value was the $650 they would make. The likelihood they would make that amount is the 98%, 0.98. Add it with the other option, which is they make $150 for a defective machine. And that happens 2% of the time, 0.02. So I'm going to multiply those, see what values I get, and then add them up. So 650 times 0.98 is 637. 150 times 0.02 is 3. When you add those up, you get 640. So we want to explain what that means in that situation. So the company will make $640 per machine sold. So yep, it's not the 650, right? Because some of the machines they sell are going to require repairs, but we've included that. So in the long run, for all the machines that they sell, many machines, they would expect for each machine it to come out to be $640 each.